Imagine it is 3 a.m. and your production environment just went dark because 50 of your custom AI tool connectors crashed simultaneously. This is not a hypothetical disaster, it is the reality of today's fragmented AI integration landscape. You may have spent months building bespoke REST wrappers for Jira, GitHub, and internal databases, only to realize that every time an upstream API changes its schema or an LM provider updates their tool calling format, your entire agent ecosystem breaks. In professional architecture, we call this a lack of a unified interface. You are essentially building a separate adapter for every single appliance in your house. The maintenance cost eventually exceeds the value the AI provides, leading to what I call the silent collapse of custom AI plugins. This is exactly where most enterprise AI projects fail before they even reach the scaling phase. But what if there was a way to stop this madness and build a bridge that never needs rebuilding? By the end of this lecture, you will understand why the Model Context Protocol is the only way to escape this cycle of technical debt and architectural fragility. Instead of writing specific code for Claude to talk to your SQL database, and then rewriting it for Cursor, and then again for your custom internal agent, the Model Context Protocol introduces a standardized host-client-server architecture. Think of it as a universal translator for AI. You build one MCP server, and it instantly becomes visible and usable across any platform that supports the standard. In a real-world production environment, this means your infrastructure team can maintain the data connectors while your AI team focuses on the prompts and logic without stepping on each other's toes. This separation of concerns is the hallmark of a mature architecture. If you are still building custom tools for each LLM provider, you are building a house on shifting sand. With MCP, you are building on a concrete foundation that is vendor agnostic and highly reusable. But this is not just about convenience, it is about interoperability and the future of how AI interacts with the world. This approach is the only way to ensure your AI agents do not become obsolete the moment a new model is released. This way is the path to a robust AI strategy. This approach seems great, but how does this actually differ from a standard REST API? Let's look at the evolution of these connections to find out. To understand why MCP is revolutionary, we have to look back at how we got here. In the early days of LLM integration, we were literally hard-coding prompts to tell the model how to use a tool. Then we moved to tool calling using REST APIs, which was better but still required heavy manual mapping for every new model and every new provider. Now we are entering the third era, the protocol era. Just as TCP/IP allowed disparate networks to communicate without knowing each other's internal hardware, MCP allows LLMs to interact with data sources without needing to know the specific implementation details of the underlying system. This is not just another API, it is a structural foundation by JSON-RPC 2.0 to ensure predictable, stateful, and secure communication. If you look at the history of software, the winning technology is always the one that lowers the barrier to interoperability while maintaining strict standards. MCP is that winning standard for the age of AI agents. It effectively turns your data sources into living extensions of the LLM brain. Is this another layer of complexity, or is it the ultimate solution to technical debt? Let us compare the costs directly to find the answer. Let's be brutally honest about technical debt in the AI space. When you build proprietary connectors, you are signing up for a lifetime of maintenance. Every time an LLM provider updates their SDK, you are back in the trenches debugging. With MCP, that burden shifts to the protocol itself. In professional practice, projects often die simply because the glue code becomes more complex than the actual business logic. By adopting MCP, you are investing in an ecosystem where the community and the providers handle the heavy lifting of compatibility. You write the tool definition once, and the protocol handles the handshake, the resource discovery, and the sampling. This is not just about saving time, it is about architectural integrity. We are moving from a world of custom scripts to standardized services. If you don't make this switch now, you will find your AI infrastructure is a legacy mess by next year. But how does this protocol actually look under the hood? In the next chapter, we are going to tear apart the three-layer architecture of MCP, the host, the client, and the server to see how they actually communicate. In the field, most developers mistake MCP for a simple API wrapper, but it's actually a sophisticated three-tier orchestration. At the top, we have the MCP host. This is the environment the user interacts with, like Claude Desktop or an IDE. The host doesn't talk to your data directly, it houses an MCP client. This client acts as a mediator, establishing a bridge to one or more MCP servers. These servers are the ones actually touching your local files, databases, third-party APIs. Why this complexity? Because it creates a security sandbox. The LLM only sees what the client allows, and the client only knows what the server exposes. In high-traffic production environments, this separation is what prevents your sensitive database schemas from being leaked into the model's global training data. It's about maintaining a strict boundary between the brain and the hands. But how exactly do these three entities speak the same language without a proprietary API? We need to look at the transport protocol. Real-world architects don't care about marketing buzz. They care about the wire format. MCP sits on top of JSON-RPC 2.0, a battle-tested, lightweight communication protocol. This choice is deliberate. Whether you are communicating over standard input-output for local processes or using server-sent events, SSE, For remote servers, the message structure remains identical. This means your server logic doesn't change based on where it's deployed. When you debug an MCP server, you're looking at clear, readable JSON objects, requests, responses, and notifications. This transparency is vital. When an agent starts hallucinating, you can instantly check the logs to see if the server provided bad data or if the model misinterpreted the correct data. In practice, the transport layer is usually hidden by the SDK, but understanding that it's just STO means you can test your server with a simple terminal pipe. Even with a clean transport layer, there's a lurking monster in AI integration: session state. How does MCP avoid the memory explosion problem? In traditional systems, state management is the architect's biggest headache. If you try to shove the entire state of a database into an LLM's context window, you'll hit a wall or go broke on token costs. MCP solves this by enforcing a stateless server philosophy. The server doesn't need to remember who the user is or what was asked 5 minutes ago. Instead, it provides resources pointers to data that the client can fetch on demand. Think of it like a REST API, but for an agent's memory. The host manages the conversation history and decides which state from the server is currently relevant. If a server process restarts, it doesn't break the conversation because the session context lives in the host, not the server. This architecture allows you to thousands of users without your servers bloating. However, architecture is nothing without content. How does the client know what the server can actually do? This is where the discovery handshake becomes critical. The magic of MCP begins with the handshake. When an MCP client connects to a server, it doesn't just guess what's available. It calls list tools and list resources. This is a dynamic capability negotiation. If you update your server code to add a new Slack integration tool, the next time Claude starts, it instantly knows it has a new capability without any manual configuration on the model side. In your code, you'll see these listed as JSON schemas. These schemas are the most important part of your implementation. They tell the LLM exactly what parameters are required and what each tool does. If your schema is vague, the agent will fail. Professional architects spend 80% of their time perfecting these descriptions because they are the documentation the AI reads to function. Listing tools is easy, but what if the server needs the LLM to think more? This is the sampling API, the most misunderstood part of the MCP spec. Sampling is the inception of MCP architecture. Traditionally, a server is a passive entity. It waits for a request and gives a response. But with the sampling API, an MCP server can turn around and ask the host to run a completion on its behalf. Imagine you are building a server that refactors legacy COBOL code. The server can send a sampling request to the host saying, "Hey, use your LLM to summarize this logic before I apply my transformation rules." This allows for recursive intelligence where the server manages the heavy lifting of the logic, but delegates the reasoning back to the model. It's a massive shift in how we think about agentic workflows. Instead of the model doing everything, the model becomes a subservice for your specialized server. Now, you might be thinking, isn't this just RAG with extra steps? Let's dismantle that myth by comparing MCP-driven context with traditional vector search. People ask me if MCP replaces RAG. The answer is it evolves it. In traditional RAG, you're fishing in a dark pond with a vector hook, hoping the top results contain what you need. In MCP, the context is mounted as a live resource. MCP provides structured, real-time access to file systems, active Slack channels, or live logs that RAG systems struggle to index effectively. While RAG is great for static knowledge, MCP is for operational intelligence. In an MCP-driven architecture, the model doesn't just read a snippet. It can explore the directory structure or query a database to find the relevant context itself. This active discovery reduces the noise in the context window and leads to much higher accuracy. We've seen this reduce hallucination rates significantly in DevOps automation. Now that you understand the 3-layer blueprint, it's time to stop theorizing and start building next, while construct a real GitHub MCP server from scratch. Choosing the wrong SDK for your MCP server can lead to a maintenance nightmare before you even ship your first tool. In the field, we generally see 2 paths, the TypeScript SDK and the Python SDK. If you are building high-performance, web-integrated tools, TypeScript is the gold standard because the MCP core itself is built with it, ensuring get the latest protocol updates first. However, for data-heavy architectural analysis or ML-integrated agents, Python's ecosystem is hard to beat. But here is the reality. Many developers treat this like a standard REST API, which it is not. You are building a stateful JSON-RPC bridge. In an enterprise environment, your choice depends on where your existing libraries reside. Don't just pick what's trendy. Pick what allows you to handle asynchronous I/O without blocking the LLM's thought process. If your SDK choice bottlenecks the I/O stream, your AI agent will time out or worse, hallucinate the missing data. But wait, how do we actually tell the LLM what our server is capable of doing? The most common reason AI agents fail to use tools correctly isn't the logic, it's a poorly defined schema. When we define a tool for GitHub, such as create issue, the description field is actually a prompt for the LLM. It is not just for documentation. It is an instruction. If your description is vague, Claude will pass the wrong arguments. We use JSON schema to strictly define parameters like owner, repo, and body. In professional practice, we use Zod and TypeScript to enforce these types at runtime, ensuring that if the LLM makes a mistake, the server catches it before hitting the GitHub API. Notice how we specify required fields. This forces the LLM to ask the user for missing information rather than guessing. But even with a perfect schema, things go wrong in the real world. This is where most developers fail. They don't handle the what-if scenarios when the API returns an error. What happens when the repository doesn't exist? In standard software, an error usually results in a 400 or 500 status code and a log entry. In the MCP world, an error is a conversation. If the GitHub API returns a 404, you shouldn't just crash. You must return a structured error message that the LLM can interpret. Instead of saying not found, you tell the agent, repository X not found. Please check the spelling or confirm your access rights. This allows the agent to self-correct, perhaps by searching for the repository name first. We call this graceful degradation. When implementing the GitHub MCP server, we wrap our API calls in try-catch blocks and map technical errors to instructional feedback. This is the secret to building resilient agents. If you provide a generic error, the agent will just keep trying the same failing command until it hits a rate limit. But how do you verify this logic without constantly burning LLM tokens during development? The most vital tool in your belt isn't Claude itself, it's the MCP inspector. Many developers try to debug their servers by connecting them directly to the Claude desktop app immediately, which is a mistake. When you use the inspector, you create a controlled environment to test your JSON-RPC methods. It allows you to simulate tool calls and view the raw protocol traffic. One critical tip from the field: never use console.log for debugging in an MCP server. Since MCP typically uses standard input-output for communication, any stray log message will corrupt the JSON-RPC stream and break the connection. Use the inspector to verify that your schemas are being parsed correctly and that your error responses are valid JSON. Once your server passes the inspector's tests, you're ready for the real-world connection. But wait until you see the configuration mess that happens when you try to move this to the desktop app. Now we move to the wiring phase. To make your local GitHub server visible to the Claude desktop application, you have to modify the Claude desktop config JSON file. This is the bridge between your code and the AI's brain. You define a MCP server's object where you specify the command to run usually node or Python and the path to your entry point. A common pitfall here is using relative paths. Always use absolute paths, or the desktop app will fail to spawn the child process. Also, ensure your environment is correctly set up so that node is in the system's path. If the Claude app starts up and you don't see the hammer icon, it usually means there's a syntax error in this JSON file or the path is wrong. This configuration is the foundation, but how do we handle the sensitive GitHub tokens that this server needs to actually work? Security is the #1 concern when building custom MCP servers. In my experience, the fastest way to get a security audit failure is to hard code credentials in your config file. While the Claude config allows an env object, it's best to use environment variables or a dedicated secret manager. Your MCP server should expect these variables to be present in its environment. When the Claude desktop app launches your server, it injects these variables into the process. You must ensure the GitHub Personal Access token has the minimum scope necessary. Don't give it full admin access if it only needs to read issues. This follows the principle of least privilege. If your agent is compromised via a prompt injection, the damage it can do is limited by the scope of this token. Now that we're secure, let's see how the agent actually orchestrates multiple tools at once. The magic happens when you give a single prompt that requires multiple tool calls. For example, summarize the last 5 issues on GitHub and write a bug fix for the most urgent one. In this scenario, Claude uses the list issues tool from your MCP server, processes the text, identifies the bug, and then uses the local file system tool to write the fix. This is multi-tool orchestration. As an architect, you need to watch the latency here. Every tool call adds a round-trip delay. If your MCP server is slow to respond, the entire agent experience feels sluggish. In the field, we optimize this by ensuring the MCP server provides exactly the data needed, no more, no less. If you dump a 5 MB JSON payload to the LLM, you'll hit context limits and waste time. Keep it lean. But what if you aren't using the Claude desktop app? What if you want this same capability in your IDE? The beauty of MCP is that it is a standard. Once you've built this GitHub server for Claude, you can use it in AI-powered IDEs like Cursor or Windsurf with almost zero changes. These tools are increasingly adopting MCP as the unified way to extend their agents' capabilities. Instead of writing separate plugins for every IDE, you maintain one MCP server that provides a GitHub context to any compatible client. This is how we scale AI integration across a development team. We build a server registry of internal tools DB access, Jira integration, CI/CD controls, and every developer plugs them into their IDE of choice. This portability is why MCP is winning the protocol war. But as we move from local desktop experiments to enterprise-wide deployment, we face a new set of challenges: scaling, concurrency, and remote hosting. That is exactly what we will tackle in the next chapter on scaling MCP in the enterprise. In the early days of AI adoption, many assumed that just because an LLM is smart, it would understand security boundaries. In production environments, we quickly learned that an MCP server connected to your core database is a massive liability if not properly sandboxed. Imagine a scenario where an indirect prompt injection, perhaps a malicious comment in a GitHub issue, tells the agent to fetch all records from the user's table and summarize them. Without a strict security perimeter, your MCP tool becomes a data exfiltration pipe. The reality is that the LM doesn't have a moral compass. It follows instructions. We must enforce least privilege at the protocol level, ensuring the MCP server only has access to specific schemas and utilizes read-only credentials by default. This isn't just about code, it's about architectural integrity. But what happens when the agent actually needs to write data? That's where things get dangerous. Designating write actions in an MCP architecture is like handing a loaded gun to a toddler. No matter how clever the toddler is, you want your hand on the safety. In professional practice, we never allow an AI agent to execute destructive actions like drop tably or delete a user without an explicit human-in-the-loop mechanism. This is where approval gates come in. Architecturally, when an agent calls a write tool, the MCP server shouldn't execute it immediately. Instead, it should return a pending approval status and a unique transaction ID. The client UI then renders a confirmation button for the human operator. Only after a manual yes does the protocol complete the handshake. This pattern prevents hallucinated disasters and ensures accountability. But even with a human in the loop, you need a way to prove what happened after the fact. How do we track these silent interactions? In an enterprise setting, I don't know why the agent did that is an unacceptable answer for an architect. Standard application logging is insufficient for AI agents because the logic is non-deterministic. We need deep observability into the MCP request-response cycle. Every interaction must be logged with specific metadata: the original prompt, the tool's input arguments, the raw response from the MCP server, and crucially, the model's reasoning trace. If a tool fails or provides incorrect data, you need to know if it was a protocol error, a network timeout, or a model hallucination. We use structured audit logs to track the intent vs action gap. This data is the lifeblood of postmortem analysis and agent fine-tuning. Security and auditing provide the foundation, but even a secure system is useless if it's too slow or costs too much to run. Let's look at the performance bottlenecks. The most common performance killer in MCP implementations is context stuffing. I've seen teams build MCP servers that return a 50 MB JSON dump for a single query. When you feed that back into a model like Claude, you're not giving it more context, you're drowning it in noise. Not only does this skyrocket your token costs, but it also triggers context overload, where the model starts ignoring the middle part of the data or loses track of its original goal. Smaller context models might crash entirely. As an architect, you must realize that every byte returned by an MCP server is a byte you pay for in LLM processing time and money. The goal is signal, not volume. But how do we maintain the necessary information while cutting the bloat? The answer lies in how we design our server-side logic. To combat context bloat, we apply selective filtering and pagination at the MCP server level. Instead of a tool named getAllLogs, you design tools that require parameters like limit, offset, and search query. This forces the agent to behave like a disciplined developer, querying only what is necessary. For example, if an agent needs to find an error in a 1 GB log file, it should call a tool that searches for a keyword and returns the surrounding 10 lines, rather than the whole file. Implementing this requires the MCP server to handle the heavy lifting of data processing. By keeping the context window lean, you ensure the model stays focused on the task at hand. However, efficient code is only half the story. The underlying infrastructure can still create massive bottlenecks. Infrastructure sizing for MCP servers is a critical trade-off between cost and responsiveness. In enterprise environments, the cold start problem is real. If you deploy your MCP servers as serverless functions, a 5-second cold start might cause the LLM agent to time out or assume the tool is broken. For low latency requirements, persistent MCP servers running in containers or as sidecars are often mandatory. We've seen persistent services outperform serverless by a factor of 10 in terms of multi-turn conversation reliability. You must balance the overhead of maintaining always-on services against the risk of agent failure. We've covered the battle scars of scaling, but are you ready for the final 2026 checklist to ensure your architecture survives the next wave? Let's move to the architect's checklist for 2026 to see if your design is truly future-proof. When architects first encounter the model context protocol, the most common trap is building a God server. I've seen teams try to bundle every internal database, their company Slack, and 5 different legacy APIs into a single monolithic MCP server. This is a maintenance nightmare. In the field, we see that tight coupling like this destroys the very modularity MCP was designed to provide. If your God server goes down, your entire agent's capability suite vanishes. Furthermore, JSON-RPC transport overhead increases as the tool list grows, leading to latency issues that frustrate the LLM's reasoning process. Instead, you should architect around micro MCP servers, separating concerns by domain. Think of one server for cloud infrastructure and another for internal documentation. This allows for independent scaling and granular security permissions that reflect real-world organizational boundaries. But wait, if we decouple everything into microservers, doesn't it become a networking nightmare to manage all those connections simultaneously? The second biggest mistake is what I call semantic laziness. Look at your tool descriptions. If you name a toolkit user and provide a vague description like fetches data from the database, you are asking for trouble. In a complex 2026 agentic environment, The LLM needs precise semantic mapping. Experienced professionals know that the LLM uses these descriptions to decide which tool to call. If the description is ambiguous, the model will hallucinate parameters or fail to trigger the tool at the right time. For example, instead of search files, use search markdown docs in Finance V2 and explicitly state that it requires a date range and category ID. You must treat these descriptions as a formal contract between the model and your infrastructure. I often suggest including few-shot examples directly within the tool schema to guide the model on edge cases. Use the JSON schema examples field to show valid input patterns for complex queries. This reduces the cognitive load on the model and significantly boosts reliability. Now that your tool definitions are sharp, how do you decide if MCP is actually the right protocol for your specific project? A question I get asked constantly: should I use MCP or stick with standard vendor-specific function calling? The answer depends on the gravity of data and your long-term lock-in strategy. Vendor for functions like those from OpenAI or Anthropic are great for quick, cloud-hosted prototypes. But as soon as you deal with local files, private VPCs, or cross-platform agents that need to work across different LLMs, MCP becomes mandatory. Think of MCP as the USB port for AI agents. If you build on MCP, you aren't tied to one model provider's proprietary API structure. From an architect's perspective, MCP offers superior security because it separates the transport from the capability. You can run a local MCP server that accesses your sensitive SQL database while the LLM lives in the cloud, ensuring that the LLM never sees the database credentials, only the tool schema. This selection matrix I prepared shows that for enterprise scale, the interoperability of MCP outweighs the initial setup speed of vendor functions. The choice seems clear now, but the real challenge is timing your migration for the 2026 landscape. By 2026, the AI infrastructure will move from API first to agent first. This means your legacy middleware must be converted into MCP-ready assets. As an architect, your roadmap should focus on 3 pillars: transport, context, and security. You need to decide where to use STIO for local high-performance tools and where to use SE, server-sent events, for remote, long-running processes. Start by auditing your current REST APIs. Could they be wrapped in an MCP server to provide better context to an agent? The MCP inspector tool should be a staple in your CI/CD pipeline to validate tool schemas before deployment. We are moving toward a world where the universal connector is the default assumption, not an afterthought. In our final chapter, we will look at how this all comes together to form the universal connector era, where the friction between data and intelligence finally disappears. But before we wrap up, have you considered how these MCP servers will discover each other in a decentralized network? To wrap things up, let's look at where you should start your journey in this rapidly evolving ecosystem. By 2026, the Model Context Protocol has moved far beyond a niche experiment. If you head over to the official MCP GitHub organization, you'll find an extensive collection of open-source servers ready for production. We are talking about pre-hardened connectors for PostgreSQL, Brave Search, and even complex enterprise tools like Jira and Slack. Don't waste your senior engineers' time writing boilerplate fetch calls. Instead, leverage these community-driven standards. In the field, the bridge pattern is the only way to survive the coming wave of AI agents. You should also look into the TypeScript or Python SDKs, specifically version 1.2 or higher, which provide the robust JSON-RPC handling we discussed earlier. The real power lies in the standardized package managers that allow for seamless installation of these servers across different environments. By contributing your own internal tools as MCP-compliant servers, you're not just coding, you're building a reusable corporate knowledge base. But wait, even with all these tools, there is a fundamental shift in architectural leadership required for this to actually work. Let's look at the final strategic roadmap. This is the final call to action for every architect and lead developer watching this. We are entering the universal connector era, where the barrier between logic and context is finally dissolving. If you continue building siloed, proprietary integration layers for every new LLM, your system will be obsolete by the time it hits production in late 2026. The technical debt of agent spaghetti is the single biggest risk to AI ROI today. My advice from years of system design is direct. Start by auditing your existing internal APIs and wrapping the most critical ones in an MCP layer. This move turns your static data into a dynamic resource that any compliant agent, whether it's Claude 3.5 or a specialized local model, can interact with safely and predictably. Architectural leadership in 2026 isn't about knowing the most APIs, it's about defining the most efficient protocols. Standardize your AI bridge today, or prepare to spend the next year rebuilding what you thought was finished. Now that we've covered the how and the why, the rest is up to your implementation. This is how you lead the AI transformation instead of just following it.